This video deals with heat and energy, the transfer of heat and energy, and the expansion of materials due to change in temperature. Now, heat is the exchange of energy between two objects because of a different temperature. So heat is the exchange of energy. Is the exchange of thermal energy. Thermal energy is the internal energy of an object due to the motion of its molecules. So the molecules are moving around, kinetic energy. Now, temperature is the measure of the concentration of the object's internal thermal energy. So how much thermal energy does it have gives you its temperature. And heat is the exchange of that energy. Temperature conversions. Now there's a couple of different units of temperature: Kelvin, Celsius, and Fahrenheit. Kelvin is the unit of temperature most often used in physics. 0 Kelvin is absolute zero, which is where the molecules stop moving. You can calculate temperature in Kelvin by adding 273.15 to the temperature in Celsius. Temperature in Celsius is the second most popular measurement of temperature. Now, if you're dealing with change in temperature, any physics equation, if you're dealing with a change in temperature, it doesn't matter if you're using Kelvin or Celsius because the change will be the same. Now, Fahrenheit is never used in physics calculations and rarely seen in science at all. But if you happen to see Fahrenheit, it's 9/5 times the temperature in Kelvin plus 32 will give you your temperature in Fahrenheit. Now, thermal expansion. When most materials get hotter, they expand. The amount they expand can be calculated, so it gets bigger. We calculate it by taking the initial length, L0, multiplying it by the coefficient of linear expansion, which is a constant depending on the type of material. For example, the coefficient of linear expansion will be different for brass than it will be for gold, etc. And delta T is the change in temperature, and because it's the change in temperature, it can be in Kelvin or Celsius. You'll get the same answer. Change in L is your final length minus your initial length. Okay, so what you ended up with minus what you started with. So if you're looking for how big it is at the end, you're going to want to add your change to your delta L. Or if it got smaller, you could subtract it. The question may ask you for a change in length or the final length, so be careful what you're looking for. Units for length must be the same, but because they can cancel out, it doesn't matter if you're in meters or centimeters or what. And same with temperature. Kelvin and Celsius doesn't matter. Here's a table from your textbook. For the coefficient of linear expansion, it's table 10.1 in your textbook. So you can get a copy from it from your textbook. You can get it online in the ebook, and a copy is also available for your printing. You may need some of those values for homework. Now let's look at an example. You have a ring with a diameter of 0.2. So the length of the ring's diameter is 0.2 meters. I also have a brass ball with a diameter of 0.19. What temperature would you have to raise the ball to in order for it to not fit through the ring? So you would need to change your length by 0.01 meters. Okay, to get from 0.19 to 0.2. Now it's a brass ball, so the linear expansion for brass is 19 times 10 to the negative 6th. So alpha equals 19 times 10 to the negative 6. And our initial length is 0.19. So we would say, all right, 0.01 equals 19 times 10 to the negative 6th times L0, which is 0.19, times change in T. And we just solve for our change in temperature. So we would have to raise our temperature 2,770 degrees. which makes sense because if you think about it, I mean 0.01 meters is the same thing as 1 centimeter. So to increase our diameter 1 centimeter, we'd have to raise it almost 3,000 degrees. Now we talked about heat energy being transferred. Heat energy is transferred in different ways. One way is conduction. Heat energy is transferred through conduction. It's the transfer of kinetic energy through molecules, atoms, or electrons. So conduction requires contact. So it conducts through a material. Starts at one end of a material and works its way through, and it goes bumpy, bumpy, bumpy until it makes it to the other end. Another way that heat energy is transferred is by convection. Convection conveys the energy to you. It's heat transferred by fluid such as air or water. When heated, fluid is caused to move away from the source, so hot fluids rise and carry the energy with them. The third way is radiation. Radiation is heat energy transfer through electromagnetic waves. For example, the sun heats us through radiation. Radiation, not convection. The convection currents rise. Okay, so this picture is a great picture to show you the difference. Conduction, well, this conducts the material through, conducts the heat through the material. Convection takes the air, heats it, and air rises when hotter, so it warms your hand. But you also feel heat over here, and that's due to radiation. Okay, that's due to the waves spreading out from the fire, because the energy wouldn't naturally transfer or, move in that direction. So that's radiation. Radiation deals with electromagnetic waves, which are the same waves that make up light and microwaves and radio waves. Now, heat energy is transferred. What is the rate of heat energy transfer? How fast does it do it? The rate of heat energy transfer is measured in watts. Right? Power, energy per time, watts. And it's how many joules of energy is transferred from one side of material to another every second. Now, K is thermal conductivity, and that is dependent on the type of material. A is the area of the material that is exposed to the heat. T is temperature. Now, because it's change in temperature, it can be in Kelvin or Celsius. And L is the thickness. How far does that heat have to travel through the material? And that's measured in meters. And area is in meters squared. Now, let's look at an example. In order to stay warm, a diver often wears some sort of thermal protection, like a wetsuit. Often, this material is neoprene, foamed material which traps gas bubbles as an insulating material. For this problem, assume thermal conductivity of air is 0.05. So our K equals 0.05. Our thickness is 3 millimeters, which is 3 times 10 to the negative third meters. The area is 2 meters squared. The initial body temperature is 37 degrees Celsius, and the water temperature is 7 degrees Celsius. So our change in temperature is 30. So we know change in temperature, we know A, we know L, because that's the thickness, 3 times 10 to the negative third, and we know K. So the question is, what is the rate of heat energy transfer? Well, heat energy transfer equals Ka delta T over L. So we plug in everything, and we can find that H equals 600 watts. Now, how much energy will the diver lose in the water in an hour? Well, 600 watts. 600 watts, not 6,000 watts. Well, power, or H in this case, is work divided by time. So we're looking for energy, which is power times time. So 600 times the time in seconds for 1 hour. Well, that's 60 seconds in a minute and 60 minutes in an hour. That gives us 600 times 60 times 60, which is 216,0000 joules of energy. All right, that's it for the lesson. Good luck on your homework.